All right, we will start with expected utility. All right, so basically, expected utility, as you all should know, is simply average utility. That is, the expected utility of a variable outcome x is simply the chance. It's just simply the chance of x1 happening multiplied by the utility of x1 plus the chance of x2 happening multiplied by the utility of x2, and so on, so on, so on. So it's really just an average. And expected utility theory says that people make decisions by comparing this expected utility. So you would choose x over y if the expected utility of x is bigger than the expected utility of y. This model is very simple. That's why it's so appealing. All you need is an average. You need the probabilities, the payoffs, the utility function. You're good. You have a decision rule. So that's expected utility. Now, since different people make different decisions, this is accounted for by having different utility functions. So in particular, the utility function depends the risk preference. And in a very simplified manner, you have at least three cases. You have the case of risk neutral. That's the first case. The case of risk neutral. The case of risk neutral is the case when you don't care about risk. Now, if you don't care about risk, what that means? What that means is you're essentially just caring about the average value, right? Doesn't matter whether you get very high X sometimes, very low X sometimes, or you just get the constant X every day. All you care is the average. That's risk neutral. So risk neutral, mathematically, is to say that your utility function satisfies the following property. Any so I'm using capital. So the combination of any 2 points, right, is the same as the utility of the combination of the 2 points. 1 minus alpha x2. All right. So that's risk neutral. You just care about the average. And graphically, it's just a straight line. Okay. So that's risk neutral. Second, you have risk averse. Risk averse means that you prefer a stable outcome over a risky outcome with equivalent average value. Mathematically, that's the same as saying the average utility, so alpha times u of x1 plus 1 minus alpha times u of x2 is smaller than the utility of the average. So that's risk averse. Any utility function that satisfies this property is a risk averse utility function. Graphically, it's a concave function. And finally, you have risk loving or risk seeking. And this is just the opposite case of risk averse. So mathematically, it's also just opposite. You prefer having risk than not. So you prefer average of utility over the utility of average. Mathematically, graphically, this is a convex function. Okay. Now, in finance, almost always you assume people are risk averse. A lot of financial theories would make no sense if you assume anything otherwise. Okay. Now, traditionally, risk-loving behavior is used to describe someone like a gambler. However, in behavioral, as there are more and more behavioral economics research, we see that it's not a very good way of describing gamblers, because gamblers do exhibit risk aversion too. So they're not necessarily risk loving. Nevertheless, they are willing to take on risk. And it's part of this course is about why people take on risk despite the fact that they're risk averse. Okay. All right. So that's risk. Now, next, once again, we're just going to be, so we're going to talk about how to measure risk aversion. So this is just served to be a very quick review. Measuring risk aversion, there are two main ways of measuring risk aversion. One is called the absolute rate of return, absolute rate of risk aversion, and the other is called the relative rate of risk aversion. Okay, the absolute rate of risk aversion is defined as usually sometimes you use the A symbol to represent it. It's negative U prime prime x over U prime x. So the second derivative of the utility function over the first derivative of the utility function. Intuitively, what does this represent? Now, if you think about it, the first derivative is the slope, right? It's the slope. The second derivative is the slope of the slope. So that's the curvature, right? So the absolute rate of risk aversion is, in some sense, a normalized curvature measure, right? And since we know that risk aversion depends on the curvature of the utility function, that's why this is a measure of risk aversion, right? It's negative because we want a positive number for risk aversion. Utility, the first derivative of utility represents how utility goes up or down depending on what you get. Now, typically we think people like, in finance, think people like money. So if X is money, you want the first derivative to be positive, right? People like money. The second derivative is the curvature. And in the case of risk aversion, the curvature is negative because utility is slowing down. So it is a negative number. And because we want a positive number for the measure, we add a negative sign in front so that for cases where the individual is risk averse, it's going to be a positive number. It's very interesting because people are fascinated with positive numbers. People like positive numbers. Another example, price elasticity of demand. You should have learned in microeconomics that the price elasticity of demand is usually written as a positive number, despite the fact that demand curve is always negative. So it's just the fact that people like positive numbers. Another theory I have about this is that economists are lazy. They would rather not write the negative sign if it's always there. So that's the absolute rate of risk aversion, and you have the relative rate of risk aversion. Now, the relative rate of risk aversion is defined as the absolute rate times X. Now, remember, X is usually something like wealth or income. So that's negative U prime prime X, U prime X times X. Now, why do we need the relative rate of risk aversion? The reason is, notice that the absolute rate could very well be a constant number sometimes, right? It could be so in particular, the absolute rate is saying that your risk preference only depends on the outcome in concern. So let's say X is the money you're gonna get. X is the money you're gonna get. What this says is someone with a lot of money is going to have the same preference over an investment opportunity as someone who is poor. Now that doesn't make too much sense, because let's say an investment requiring investment with a risk with 1 million at risk. An investment with 1 million at risk, it's a very big investment for us, but it's not a very big investment for like Bill Gates or Li Ka-shing. So it's not very realistic to assume that Bill Gates and I have the same risk preference over the same investment project or same stocks. So the relative rate of risk aversion allows for one way where Bill Gates and I can differ, namely our wealth. X. Okay. If you take so typically relative rate of risk aversion is more realistic. What it allows is people with more money would be willing to take on more risk. Okay. One way of looking at it is this. Absolute rate of risk aversion means that you have a constant dollar amount you want to invest, just regardless of your wealth. Relative rate of risk aversion, on the other hand, means that you have a constant fraction of your wealth you want to invest. So since Bill Gates is so much more wealthier than I am, so even if we both have the same relative rate of risk aversion, we could be investing in vastly different amount of money because he is richer. Okay. In financial theories, you would see two utility functions that used it very often. The first is the constant absolute risk aversion utility function, and the second is the constant relative rate of risk aversion utility function. So the first is the constant absolute rate of risk aversion utility. So this is usually shortened as CARA. You hear this a lot, CARA. And what it does is it's a utility function that satisfies the property where the absolute rate of risk aversion is constant. Now, and it looks the following way. So the utility function is negative exponent to the power negative AX over A, where A is a parameter you can choose. So usually it's going to be a positive number. This utility function has a property where the absolute rate of risk aversion equals to A. So you'll be asked to show this to be true in the first assignment, but even if you need to derive it from scratch, it's not very difficult. It's simply an application of differential equation. So it's very simple to derive. But it's quite easy to verify it's true. The other one that's very common is the constant relative rate of risk aversion utility. Constant relative rate of risk aversion utility, and this is commonly called as CRRA. And once again, you hear this term a lot, CRRA. So this one looks like this. The utility function is x to the power 1 minus r over 1 minus r. And it has a property where the relative rate of risk aversion is going to be r. Okay. So these two are essentially the only utility functions used in many cases. Because why? Now, there are practical concerns. Since so first, they are relatively simple functions, right? It's just basically in one case you have an exponent, in the other case you just have a power. So they're relatively easy, and they have quite nice statistical properties, so that it's easy to use. Furthermore, in empirical finance, if you need to fit a model, right, the more parameters you have, the harder it would be. These two utility functions both only have one parameter, which makes them very attractive. In this course, we usually use the absolute rate of risk aversion. The reason is it's easiest to use. It's really, truly easy to use. So that's what we use a lot of times, even though the CRRA utility is probably more realistic. Now, how easy is it to use? How easy is it to use? So, we are just going to go over an example of how to maximize a CRRA utility in an investment situation. So the simplest investment situation is the case where you have only a single risky asset. You have a single risky asset and one safe asset. Okay, so that's the simplest you can go. Because even if you think, what about not having a safe asset? If you have no safe asset, well, there is still a safe asset, namely your cash. Right? It's just a safe asset that returns a zero return. So it's not possible not to have a safe asset as long as you can keep your cash. What about not having a risky asset? Well, if you don't have a risky asset, then there's not much decision to make to begin with. So the simplest case is one risky asset and one safe asset. And typically, this is modeled as in the following way. Okay. Single risky asset optimization. Despite the fact that it's so simple, you will see that it actually gives us a lot of intuition. So we start with assuming that the individual has wealth W, and then there's, as I said, there's one risky asset, one risk-free asset. The risky asset has return R plus S, whereas the safe asset, so that this is a risk-free asset, return is just R. Now, in this setup, R is a fixed number, a constant. R is a constant. And S is random. Okay. So S is what we call a risk premium. It's the additional return you get, for taking on risk. To be more precise, I would say the average of it is the risk premium. That's what you get for taking on the risk. Okay. Now, if you start with wealth W, then and you decide to invest a certain amount into the risky asset, let's say invest. Now, this is the part where we have to be careful. We're going to talk about theta as the dollar amount invest. So theta is dollar amount. So to make it clear, so you're going to invest theta dollar amount into risky asset. And with this setup, the decision comes down to maximizing the amount to invest of the utility of the expected utility of. Now remember, we have W. We invest theta into the risky asset, so you have W minus theta in the risky asset, in the safe asset, which gives you return of R, right? And since you have your original asset, so that's what you have, right? 1 plus R is the return you're going to get, and plus theta into the risky asset, which gives you 1 plus R plus S. Okay, so if you know the utility function, then you take the derivative. However, there's a problem. There is the expectation. If you have discrete events, like a binary event, either stock market goes up or stock market goes down, then you can just write them all out and take a derivative. But since we know real stock markets are not discrete, so you have continuous distribution. And this is where the utility function we just mentioned are very helpful, because they have statistical properties that allow us to simplify the expectation. So we're going to use we are going to use the CARA utility. Okay, CARA utility. So need to know the distribution of S. So the case that we will use is CARA utility with log normal. Is it? Sorry, no, just normal, not normal. Okay, with normally distributed S. Okay. In this case, it turns out there's a very nice way we can break apart the expectation to allow us to use differentiation. Namely, we're going to use the following rule. So before I mention the rule, let's take a look at how the utility function would behave, right? So S is normal, right? When S is normal, R plus S is normal, right? When you add a constant term to a normal distribution, it's still a normal distribution. All right, now we put it in the utility function, right? Now you have this utility function where you have negative E, negative A, right? Negative E, negative, oh, pen stopped working. Negative A, wealth over A. That's the utility function. Now, what is wealth? As we just say, it's just negative E, negative A, a whole bunch of stuff, right? You have this is wealth. I should say this is wealth in the next period. So wealth T plus 1, right? So that's just wealth minus the amount you invest in risky asset times the return of the safe asset plus the amount you invest in the risky asset times the return of the risky asset, which is 1 plus R plus S. Now take a look. You should realize that everything in this utility function is constant except for the risk coming from the risky asset. So this whole bunch of stuff is normal because you're just multiplying a normal distribution by with constant, and then you're adding the normal distribution with constant, and both of these preserve the normality. So the whole wealth, in other words, the whole wealth is normal. Wealth is normal. And then wealth is inside an exponential function. And what does that give you? What does that give you? Well, this is it. When you have an exponential function enclosing a normal distribution, the resulting number is log normally distributed. The reason why it's called log normally distributed is if you take the log of this function, it becomes a normally distributed number. So W is normally distributed. When you take the exponential function, it becomes log normally distributed. It's just a name for this property. And here is a statistical, this is a probability theory rule. This is just something you have to remember, since we're not going to show why it's true here. The log of the expectation of something equals to the expectation of log of x plus half the variance of the log of x. Now this is just a rule. The rule applies whenever x is log normal. Okay. So this is just a rule. And with this rule, it allows us to turn the expectation of the utility function into, in some sense, utility of expectation, which is very helpful, right? Now that's what we're going to do. All right, that's what we're going to do. So the example I'm going to use is the utility function equals to negative the exponent to 4x over 4, right? Now, let me write out everything. So what you want is to maximize with respect to theta the expected utility, which is maximizing the expectation of this negative e to negative 4. I should really use w, but okay, you know what I mean. I should use w. So I'm going to write down the wealthy. So you're investing w, right? W minus theta 1 plus r plus theta 1 plus r plus s, and closing this bracket, and then close 4. Let's first simplify a bit the whole chain of terms on the top. If you rearrange the terms, what do you get? You get negative exponent of 4. I'm missing a bracket right here. I have a big bracket here. All right, so notice that you have w times 1 plus r minus theta times 1 plus r plus theta times 1 plus r. So the theta times 1 plus r should be cancelled out. So you're left with w 1 plus r plus theta s. Now this is much easier to understand. What you have is, essentially what this says is, you're guaranteed to have a 1 plus r return on your wealth, but that's adjusted by the risky return you get from the risky asset, and you have invested theta on that. Okay? All right. So this is the part where, without the rule, it's very hard to proceed further. It's very hard to proceed further. What we are going to do next is, remember, the rule requires you to have a lock and closing and expectation. We don't have that here. But fortunately, we can add that. Why? Because you should have learned in microeconomics, a strictly increasing function preserves utility, right? If you have a utility function, and you take the log of u, the resulting function represents the same utility, because you should remember that utility is a ranking. Higher number means better. Because log is a strictly increasing function, it preserves the ranking, and as a result, it's the same utility function. Or I should say, it's the utility that represents the same preference. So, what we're doing here is the maximization of utility. We can add log outside of our utility function, and will preserve the preference of the individual. However, well, at this I can skip the however until later. So let's just put in the log first. So okay, it's as simple as this. Just going to put in the log. Okay. All right. Now we can apply the rule we have. Okay, so rule is on there and on top of there, right? So remember this log preserves utility. So we good. So we can use the rule to break apart the expectation, the log of expectation, into expectation of log and variance of log. So you have expectation of log of your utility function plus half variance of the log of your utility function. Okay. And this is the part where you can start this is the part where you can almost start doing the derivative, because take a look. You have log of you have an exponent inside the log, and exponent and the log cancels out. Now you do have a 4, but as you know, log of a division simply becomes log of the top term at the top minus the log of the term at the bottom. So you can take out the 4. You can take out the 4 if you want, similar to the bottom, and so that becomes max theta expectation of log negative E W1 plus R plus theta S minus log 4 plus half variance log negative E negative 4 W1 plus R here's the part that I was not very careful, so now I'm facing a difficulty. Is that we have a log of negative number. What do we do? The best way is actually, mathematically, is to take out the negative first. I mean, now we face a difficult situation on how to argue that we can take out the negative. But so the easiest way is actually to take out the negative all the way at the top, because back when you just have an expectation, you can take out the negative as you wish, right? Now you put it in a log, then you're in a difficult situation what to do. So I just have to cheat. I'm going to go back and erase it. So the best way to do is to take out the log before we take out the negative before we take the log, because that's perfectly valid to do. The negative does not affect the maximize. Well, what it does is, instead of maximization, you have a minimization. So to be very precise, what you have is back at the step here. I should have taken out the log. So I should take the negative. So that's what I have to do, because otherwise it's just hard to argue. So it's better to cheat here. I'm just going to go back. Now, because you're now becoming a minimization, so we have to be careful what we mean. It's not equal. It's not equal. So what is true though is that the answer, the resulting theta, so argmax equals to argmean of the stuff, of this bunch of stuff without the negative sign. So this is correct. So now you can now I just have to erase all the negatives. Sorry about that. So just okay, but at least so this is, and we have to change all of them to argmean. Now, if you I haven't mentioned, so we have a teaching assistant for the course, Paul Chung. He's a second year MPhil student. He's also a graduate of our own undergraduate program. Now, he's honestly a lot better at math than I do. So if you have any questions, if you have anything that you don't understand about the theory part, you can ask him. He's a lot more careful in this kind of stuff. Okay, so this is right. So, and in case you worry about copying, I also have it typed out, so which I'll upload to eLearn later on today. Okay, so argmax theta equals to argmean theta if we remove the negative. So we are switching the sign, so we're going from maximization to minimization. But as you know, in terms of the math, when you take a derivative, it doesn't matter whether it's maximization or minimization. It affects the second order condition only. All right, finally, we are reaching a state where you can cancel out the log with the exponent, leaving you with just the items inside. Let's do an argmean. You have the expectation of -4 W times 1 plus R plus theta S. Oh, shouldn't close. Let's see. Yes, close this one. Minus log power 4, close bracket. And plus half variance E, -4 W1 plus R plus theta S. Okay, minus log 4. All right, here's the part you have to start using your statistical knowledge for the variance part. Because remember, if you have a random variable, you add a constant item, you add a constant number to that random variable, it doesn't affect the variance. It affects the average, so it affects the expectation, but it doesn't affect the variance. So the variance, actually, you can simplify further. Now here's the point where I'm getting tired about writing so many items. So I think I want to so just one more step, and we are good. We can do the derivative. Okay, -4 W1 plus R plus theta S minus log 4 plus half variance. Now here's the part where let's think about it carefully. Log 4 is a constant, doesn't affect the variance. W1 plus R is also a constant, right? Risk-free, wealth, both are the constant. So this also does not affect the variance. The only thing that affects the variance is S, and indirectly theta and 4. And in fact, the negative sign does not affect the variance too, right? The negative doesn't affect anything. So in the end, it's really just 4 theta S. Hold on. Finally, we can take the derivative. Take the derivative of, sorry, one more. Because I should also we should also try to bring as many items outside of the expectation before I take the derivative. So log 4 is a constant. You can take out of the expectation. -4 is just a constant multiplier. You can take it outside of the expectation. The W1 plus R is a constant. You can take it outside of the expectation. The only thing that you need an expectation is actually S. So a better way is just to say, so I just put the expectation here. Yeah, that's much better. Okay, so that's much better when you take a derivative. It's much easier to understand. So now you take the derivative. Okay. You take the derivative. You have, okay. So you take the derivative of this bunch of stuff. Okay. A lot of stuff. Let's see. Let me make sure I get it all right. Plus half variance 4 theta f. Okay. Take a derivative. Equate that to 0, right? And there's no theta here. This goes away. There's a theta here, so this has to stay. No theta here. This goes away. Theta here, so this has to stay. Let me make sure I have all the signs correct. I think the -4. There's a I think there should be a okay, there's a bracket here. So there's a -4 here. Yeah, there's a -4 here. Yes. So I have to be very careful. Negative, yeah. Okay. So theta is already outside of the expectation, so that's fine. We need to take this theta out. When you take a constant number outside of a variance, you have to square it, so it becomes theta square. And let's just take the 4 out at the also, so it becomes 16, right? All right. Finally, let's take the actual derivative. You get -4 ES plus 2. The 2 cancels out, right? You pull down the 2, it cancels out, so it becomes theta 16 variance S equals 0. Rearranging gives you theta equals to, what does it equals to? 4. Oh, the 4 would cancel out, so let me just skip that too. ES over 4 variance S. Okay. Done. All right. So after all this math, this is what we get. In a single risky asset situation, the amount, remember this is a dollar amount. The dollar amount you want to invest equals to the risk premium over a certain constant times the risk. What is this constant? This is the rate of risk aversion. So ultimately, it comes down to risk premium over rate of risk aversion multiplied by risk. So it's a surprisingly intuitive formula, right? You invest more if the risk premium is higher. You invest less if you are more risk averse, and you invest less if there's more risk. It's a very intuitive formula. Okay. It does, however, have some implications that you might not like. Now, the first one that is very specific to CARA is that, as you see, nothing about wealth here, right? It says that you want to invest the same dollar amount as long as the risky assets properties are the same. This is what we don't like, which is why we have CRRA. When you have basically an X in this formula. The more money you have, the more absolute dollar amount you would invest. So that's the first problem. The second problem is, notice that as long as the risk premium is positive, you would invest in a positive amount in this asset, which is to say, everyone should hold some stock. This is one way of interpreting it. Everyone should hold some stock because the stock market does return a positive risk premium. It could be very risky, but it does give you a higher return on average over the long run. So for that reason, everyone should be investing. If you think about it carefully, it does make sense because given the stock market's return over like 50 years, there's no reason why you don't buy stocks for your retirement, at least. So this is one of the puzzle in finance, which we'll talk about in a moment. But bear that in mind. Now, in reality, a large fraction of people hold no stock at all. You probably know someone who only put their money in like time deposit in certified deposits. Why? Right? Why? Finally, there is a problem with the implication of this formula in terms of the amount invest. Not just that people don't invest. Even for people who invest, they're most likely not investing as much as any economic theory would suggest under expected utility, what we will see now.